Everyone, Mr. Smith here, and in this video lesson, we're going to investigate translations of functions. And to get started, we're going to look at three basic or base functions. One of them you already know and should just have, in your math toolbox, kind of know the base function f of x equals x squared, or the basic parabola. And then some other base functions we're going to want to have down are the radical function, the square root function, and the rational function 1 over x. So we're just going to do a little exercise graphing those guys and just understanding their basic table of values. And moving forward, you guys would be expected to be able to graph these guys with these key points just automatically, no thought involved. So from grade 9, you guys know the basic parabola y equals x squared goes through 0, 0 as its vertex, and 1, 1, and 2, 4, and 3, 9. 1, 4, 9, because those are perfect square numbers. There we go. But again, you guys ideally have that ingrained from your grade 10 course. We have investigated this function, the next one, the radical function. But I want to share with you guys the key points you absolutely must know so that you could just reproduce this graph just from memory, basically. You want to have a good understanding of what this one looks like. So from our discussions with domain and range, we know that you can't root a negative number. So -3, -2, -1 are outside of the domain of this function. But the square root of 0 is 0. The square root of 1 is 1. The root of 4 is 2. And the root of 9 is 3. So I intentionally picked special x values to give me nice whole number points. So these are the 4 base points that we'll use when we're sketching the square root function. For 2, yeah, I thought that was a little high. It's like, that looks off. That's because it's way too high. 9, 3. And this function starts at 0, 0, and just kind of starts to level off and flatten off and flatten off. Like so. So this is the radical function, y equals root x, and you must know these 4 key points. But they're not too hard to remember, right? It's just you think of the first 4 numbers that can be square rooted. 0, 1, 4, 9 gives you the x, and those are the x values corresponding to 0, 1, 2, 3 for the y values. So you want to have this graph up here. But yeah, if you just looking at the function, everybody in this course should be able to reproduce these 4 points easily with the equation. And the last one we've looked at, it's the function f of x equals 1 over x. So 1 divided by x. So 1 divided by -2, -0.5. 1 divided by -1 is -1. 1 divided by -0.5 is -2. 1 over 0 is undefined. 1 over 0.5 is 2. 1 over 1 is 1. 1 over 2 is 0.5. So these are a little bit, in my opinion, less obvious than the radical function. But given this equation, you guys should be able to whip off, some key points pretty easily. These are all pretty easy divisions to do. And what does this graph look like? We've seen it before, but -2, -0.5, -1, -1, -0.5, -2. And we saw that this graph kind of looks like this down here. And then 0.52, 1, 1, and 2.5. And this graph looks like something like this up here. So these are the 3 base functions that we're going to be looking at today. And we're going to be transforming these functions. And today we're going to be looking at translations. So I won't spoil the fun what a translation is just yet. But you guys looked at translations in your grade 10 course, but you only did it with parabolas. But now we want to do it with any function. We want to be able to handle that. So I'm trying things differently today and just doing the lesson right on the handout I have, instead of like just making a PowerPoint and putting the questions in there. And then we'll see how it goes. I also plan on using Desmos quite a lot, so I just wanted to have the tabs easily accessible. All right, so these are the three base functions you got to know for today. We're going to be transforming them. So my intention for this investigation is not for you to graph these by hand. I would like you to graph these in Desmos and just graph all three at the same time. Desmos will give them all a different color. And let's see the effect of, in this case, we have the basic parabola, and then we're adding 2, and then we're adding, and then we're subtracting 4. So what you can do for these investigations, what would be preferable is if you actually pause the video and just do the entire page, and then come on back when you finish the investigation and unpause. So it doesn't kind of spoil, I don't want to spoil the fun. Here is, I'll type in y equals x squared, basic parabola. In our second graph, y equals x squared plus 2. And finally, y equals x squared plus 3. Now, I'm not going to really comment on anything just yet. I just want to get, that was minus 4 actually. I just want to just make a rough sketch. There we go. Make a rough sketch of each of these guys in my note. So I'm going to do that right now. I'm just going to draw a rough axes. Then here was the basic parabola. And then I'll use green for x squared plus 2. And it's just simply look like that. And x squared minus 4 looks something like that, like super rough. Making a rough sketch will give us a very good idea of what's happening today. Okay, now we're going to look at these three guys. I believe in Desmos, square root, yeah, it gives you the root, SQRT. And then just make sure you hit the right arrow so that we're adding 2 outside of the square root. We're not adding inside. Oh, I forgot to do the basic one. So square root x and y equals square root x over minus 4. And what we want to be looking for is similarities to what we did with the basic parabola. So let's get these down. Whoops-a-doodle. Rough axes. Very rough. That's okay. The basic function. Root x plus 2. Looked like that. Root x minus 4. Looked like that. So hopefully you got something similar when you did yours. And then lastly, we'll look at what happens when we do 1 over x. Rough sketch of the basic one, and let's see what these guys look like. Y equals 1 divided by x. Equals 1 divided by x, and make sure you're adding 2 to the end, not on the x. Y equals 1 over x minus 4. All right. And it's my hope that you could hopefully predict what those were going to look like and what was going to happen even before we did it. So 1 over x plus 2 just roughly looked something like that. And 1 over x minus 4 something like that, loosely speaking. Yeah, again, the purpose of those graphs was just to give an idea of what's going on here. So if you could summarize what the effect of adding or subtracting a constant on the end of a function is. We did that 2 times for 3 different base functions. How would you describe what effect that has on the graph? By adding 2 or subtracting 4, how did that change the graph? What happened to the graph? Well, we say this. Can I add text? Yes, I can. The graph of g of x equals f of x plus c is a vertical translation by c units. So a vertical translation. Another word for translation is shift. I don't mind using that word either. To me, they're kind of the same. But yeah, translation is the formal word. When you translate something, you are just picking up and moving it, and you're not changing its shape or anything. If the value of c was bigger than 0, like when we had plus 2, we saw that the graph translates upwards by 2 units, or by c units, excuse me. So when we had plus 2, it shifted up 2 units. And when we had minus 4, so when that value of c is negative, the graph translates downwards by 2 units. And it was 4 units on our examples. Yeah, so and hopefully that's not surprising to you from last year. Last year, you guys did this very thing only with quadratic functions, but the same rule applies with any functions, and hopefully you're convinced of that. Adding a number on the end of a function will shift that base function up or down. All right. So now we're going to look at a similar groups of functions: quadratic, radical function, rational function. But this time we are adding and subtracting a number off of the x itself. So just like last time, if you want to, it would be great for you to pause the video and get sketches of these, maybe use different color like I have. Yeah, check back in when you finish them. So I'm going to assume that you've paused the video. You don't want any spoilers because I'm going to graph these guys right now. Here we go. Basic parabola, y equals x squared. And x plus 2 squared. Note the position of where it shifted. And x minus 4 squared. So basic parabola, x plus 2 squared, moved it left. X minus 4 squared, moved it to the right. And let's just get that. I don't want to use equation. I just want to draw. There we go. Hey, I said upgrade to teacher. I am a teacher. Get out of here, Cammy. I guess, guys, you get what you pay for, right? And I paid $0 for this software. I'll expect to be interrupted by a kid in 1 second. All right, so that was that one. X plus 2 squared. I'll just draw it like this. It moved left. And x minus 4 squared went over here to the right. Maybe you had predicted otherwise, because when we added 2 on the outside of the function in our last investigation, things moved up in the positive y direction. Here, adding 2 off the x, did it move the graph in the positive x direction? No, it moved it in the negative x direction. So interesting. Let's try it with the radical function. X plus 2, all inside the square root, and x minus 4, all in the square root. Notice the direction. The graph is shifted. And I'm moving through these a little quicker because I've assumed, my assumption is that you have tried these already. There's our basic radical function. We saw that root x plus 2 moved this way. Root x minus 4 moved that away, consistent with the one above. And finally, let's look at the rational function. Clear these dudes. Y equals 1 over x equals 1 over x plus 2. This time we're adding 2 directly off the x. Y equals 1 divided by x minus 4. And did the same thing happen? It did. The red is our original. The blue is x plus 2, and you can see it has shifted to the left, consistent with what we just saw above. I guess I should draw the basic one. Didn't want to add too many on here because then these graphs can get a little clustered. So we moved left and left. And x minus 4, just getting a general idea, moved it right and moved it right. Should look something like that. More or less, it's just a rough sketch. All right, so can we summarize what we've seen there? How would you describe the effect of adding or subtracting a number directly off the x? And that's what that notation is saying. It's saying that this new function, you're taking the old function, and where there was an x, you're either replacing it with x plus a number or x minus a number. And hopefully you're convinced that doing that is it's a horizontal translation. By d units, if we say x minus d. And it just parallels what we did before. And hopefully what you notice is, so if d is greater than 0, so if you are subtracting a positive, the graph shifts to the right. Units. And if d is less than 0, the graph shifts, I guess I should say translates, to the left, d units. So just to help that sink in, think for a second, and this is just, you can just scribble this in the margin here. So here's an example. Let me take the, let's look at this function. How is this function going to be different than the basic parabola? So think about what we did above. Think about our definition here for a horizontal translation. So is the number we're subtracting positive and it goes right, or is the number we're subtracting negative and it shifts left? If you said this is a shift to the right of 5 units, good for you. So this is something that is maybe a bit counterintuitive, but you did see in your grade 10 course. The effect of subtracting a number from the x, subtracting a positive number, moves it to the right. Whereas something like x plus 3 squared, that's like x plus 3 is like subtracting a negative number. That hence this definition still makes sense. And that shifts it to the left, 3 units. So more or less, if you understand, subtracting off the x moves right, adding off the x moves left, then you're in good shape. But that is counterintuitive to for some people. Because again, like subtracting 5 in the x direction, that's x direction is to the left, right? The negative x direction. But when we subtract 5, it actually moves it to the right, which is, again, a bit counterintuitive. But hopefully you're convinced. We've just demonstrated it a bunch of times. All right. So having investigated, and hopefully you're convinced that these transformations give you translations, I've given you just some kind of like piecewise defined function here. This function doesn't really have an equation. It's just basically 3 lines all connected, but it is a function, right? It does pass a vertical line test. And I've given you 4 points on this function. Minus 3, 1. Minus 3, 1. I'm just going to fix that. Minus 3, comma 1. and minus 2 minus 2, and 1 minus 1, and 3 minus 1. And what I'd like you to do is, having learned what we just learned, what is this plus 4 going to do? What effect will it have? Well, we've been looking at translations. So what kind of translation is it? Up, down, left, right, and by how much? And I'd like you guys just to graph that transform function. And I often like to just emphasize the what the image point would be, where each point moves. So you can try that on your own if you'd like, or you can follow along with me right now. So we have these points x, y, and if you said that this is a vertical translation, good for you, by 4 units. So what happens to the y values in a vertical translation? They all get increased by 4. So the point minus 3, 1 gets moved up by 4 units. It will go to minus 3, 5. And the x values are unchanging, right? They're not changing. Minus 2 plus 4 is 2. Minus 1 plus 4 is 3. And minus 1 plus 4 is 3. Oh, and I guess, look at me, master teacher. I left room for things to be shifted up. Fantastic. So minus 3, 5, minus 2, 2, 1, 3, and we can see that it's the same shape. Nothing's changed. It's just been moved up by 4 units. Sometimes I'll have you guys do that on the same grid. Other times like this on a separate grid. But hopefully, and I think most of you guys probably just could have made the graph without finding the image point, but I think it's a good exercise to think about how the points are changing. And here they're adding 4 to the y values. So here's another exercise for you guys to do. Here's our function. First I would say this. If I just gave you the function g of x equals root x plus 4, I would expect everybody to recognize that the base function is a radical function, root x. And I gave you the graph here, but I'd expect everybody to be able to get those 4 easy points, 0, 0, 1, 1, 4, 2, 4, 2, and 9, 3. Plot those 4 points and make a graph yourself. However, for the purpose of just getting some more examples in, I've made that graph for you guys. But again, full disclosure, I would expect you guys to be able to make this graph and generate these points on your own. What is the effect of adding the 4 on the x? Again, we're studying translations. Which is it? Is it up, down, left, right, and by how much? So I'll wait a second for you guys to think about that. You can pause the video if you want more time. But if you said this is a shift left by 4 units, you would be correct. So what would that look like for the image point? If the original point is xy, if we're shifting to the left, we're going to be subtracting 4 off the x value, and the y value stays unchanged. So 0, 0 will go to minus 4, 0. 1, 1 will go to minus 3, 1. 4, 2 would go to 0, 2. And 9, 3 would go to 5, 3. And if you're not convinced, let's just sketch those points and hopefully you will see. So minus 4, 0, minus 3, 1, 0, 2, 5, 3. As you can see, same function, just moved to the left by 4 units. And this year, I wanted to try just thinking about as we do these, because I think everybody can probably visualize what's happening, but I like thinking about what happens to the image point too. I think that's a good idea. All right. I think this is our last little exercise here. So this one, we are combining a few things at once. So for each of these 3 functions, I want you guys to identify what's the base function, and then describe the transformations. Using words is okay, or dot, point form, what have you. And then I want you to sketch a graph of this function. So, and then afterwards I said state the domain and range. Let's dive in. So looking at this function g, everybody should recognize what the base function is. The base function here, the one that's being transformed, is x squared. Kind of obvious, got the squared in there. And so not a bad idea if you want to just put those dots there at those basic points. And again, everybody should have these down: 0, 0, negative 1, 1, 1, 1, negative 2, 4, 2, 4. And in this graph here, 3, 9 and minus 3, 9 are off the graph. We don't need them on there. So what are the transformations happening here? We have a vertical translation up 1 unit and a horizontal translation left 5 units. So sometimes it might be visually helpful to do one of these at a time. However, with translations, it's often easier just to take each base point and do the horizontal shift and the vertical shift all at once. So let's take each of these points, and I'm going to get a new color here. I'll do let's go to purple or magenta or whatever that is. Looks nice. So we're going to take each of these points and take it 1 up and left 5, or left 5 and 1 up, doesn't matter. So left 5, 1 up, that guy goes there. This one, left 5 and 1 up, goes here. Left 5 and 1 up, goes here. What some of you guys might notice is that, some of you guys might have just translated the vertex to -5, 1. And then because translations don't change the shape of the graph, you can just use the step pattern to finish it off. But yeah, I'll just finish off here. So this guy goes 5 left, 1 up. And that guy goes 5 left and 1 up. So you can do both transformations at the same time. And I think just because this graph isn't too cluttered, I'm just going to fill in the graph, the basic parabola. So we did that guy, and we did that guy in hot pink. I'll just show it that way. Yeah, so hopefully that made sense. And then after we have sketched it, what's the domain and range? Get out of here. What's the domain and range of this guy? Well, I mean, the pink function we drew is just a quadratic function, and you can plug anything you want into those. And the range, we can see by graphing it, the range is all the y values greater than or equal to 1. What you'll notice is that shifting up or down or left or right can change the domain and range too. Right? I think what the domain normally is for the basic parabola, it's y values that are greater than or equal to 0. When you shift that parabola up 1, the range shifts up 1 too, and now it's greater than or equal to 1. So domain and range shift along with the function, which is pretty cool. Let's do this guy here. So hopefully you guys look at this function and can recognize, hey, my base function is 1 over x. Now I'm going to add the 6 points we had earlier. So those were 0.52, 1, 1, and 2.5, and then kind of mirrored on the other side, negative 0.5, negative 2, negative 2, negative 0.5. I've got some cool talking points about this one too. All right, can you describe the transformations like we did above? Again, pause the video and give that a try, and then unpause when you're ready, or follow along. So, and it doesn't matter whether you describe the vertical or horizontal translation first, but here we do have a vertical translation. Units up, and a horizontal translation. Asher's just in the hallway getting excited about animals. Horizontal translation of 2 units to the right. So what we can do is we can pick up each of those points and move it 3 units up and 2 units right and have our graph. But I'm going to propose something else to you guys. If you recall, we had two special, we called these lines that this parabola kind of approaches, or that parabola, this rational function approaches but doesn't cross. We called those asymptotes. The original function has a vertical asymptote at x equals 0. Remember, x can't equal 0 because you can't divide by 0 here. And this whole graph is being translated 2 units right. That means this asymptote is also translated 2 units right. We have a horizontal asymptote here this graph never touches, and it is going to shift up 3 units along with the graph. So when sketching rational functions, I think it's helpful to draw the asymptotes and where they've been translated to. And now the points are actually pretty easy because they follow the same shape, right? So normally we're at 1, 1 and negative 1, 1. So it's like here and here. And then we are normally at 0.5, 0.52. So I'm just drawing kind of where those are with respect to the asymptotes because the shape does not change. And that's just how I find these helpful. Of course, you can literally, if you pick up each of these 6 points and move them up 3 and right 2, you're going to get exactly what we have for my graph. Can I undo those guys? That's a little cluttered for my liking. Hopefully it doesn't erase too much. Yeah, that's good. Good. Yeah. Yeah, big idea, guys. Hopefully you understand and can just predict which direction things can be shifted. And if we, in this case, I made an accurate graph by shifting the asymptotes first and then drawing the other points in positions where they were originally with respect to the asymptotes. But literally picking them up and just following the rule works just as well. Now that we have sketched that, let's talk about domain and range. Now, you guys should be able to identify the domain and range of this function, either from the equation or from the graph. From the graph, we can see the domain. Obviously, there's one x value this doesn't hit. And that's 3. That's 2. X can't be equal to 2. From the equation, that makes sense because you can't plug in 2 on the bottom here and divide by 0. The range, we can see the only y value you cannot get from the graph is 3. Y can't equal 3. We can get that from the equation too, because we can never get 0 by doing 1 divided by something. And because we can never get 0 with that, we can never get 3 by adding 3. So from the graph or the equation, we should be able to identify the domain and range. All right, guys, one more to do. So the base function here. And again, if you want to just pause the video and try the whole thing on your own, please do. Otherwise, I'm going to continue. But our base function here, radical function root x. Easy points. 0, 0, 1, 1, 4, 2, 9, 3. Plot the ones you can fit. And again, we want that to be second nature, almost automatic. Describe the transformations. So let's look at what's going on here. We have 2 transformations, 2 translations. Text box, there we go. So we have a vertical translation down 4 units and a horizontal translation right 3 units. Let's just pick up each of those points and move them. So 0, 0 goes down 4 and right 3 to here. Now I want you to note, because the graph keeps its shape when you translate it, you can just from here graph the same shape you had before, or you can just pick up the points and move them. Down 4, right 3. Down 4, right 3. I think for this one, I'm going to show those arrows because it's not making my graph very clunky. The graph looks nice. Down 4, left 3, that goes off the page, but that's okay, something like that. And our graph, like so. Now, that looks okay. Now, what I want to mention with the radical function is that's where the domain ends. A lot of times, students graphing the rational function, especially when they flip it, want to continue the graph down. No, the graph in this case starts at 3, -4 and doesn't go beyond that. The domain of this function, again, we should be able to get this from the graph or the equation. We can see from the graph, this graph only hits x values greater than or equal to 3. Why does that make sense in the equation? Because you can't root a negative. So the x value has to be 3 or above in order to get a non-negative number in there. In the range from the graph, we can see that the y values are greater than or equal to -4. This makes sense from the equation because when you root something, you can only get 0 or a positive. And so the absolute lowest you can get is when this is 0 and you subtract 4, you get -4. Yeah, hopefully you found that to be pretty chill. Just a little bit of graphing, not a lot of algebra. But let me stress what you guys got to know. You got to know your base functions and you got to know those key points. And then we've essentially reviewed what you knew about translations, but just showed that they just don't apply to quadratic functions. You can apply them to any function at all. I enjoyed delivering that lesson. Hope you guys enjoyed following along. Until I see you guys next time, hope you're doing well. Have a great day, and we'll see you soon.